Hello everyone, welcome to A for Analysis YouTube channel. Today we have a very interesting problem statement. Today we are going to work with a housing dataset from which we will try to analyze different properties of an housing property, and after that we will try to predict the price of that house, and that will be something useful for a real estate company which wants to enter into the Australian housing market. So the problem statement is something as follows. A US-based housing company named Surprise Housing has decided to enter the Australian market. The company uses data analytics to purchase houses at a price lower than the actual price and flip them on the higher price. So basically, we want to predict the housing price, and once we are able to do that, we will give the model to the company, and the company will try to identify the house for which the price is quite low, and they will buy those houses and they will sell them at a higher price. So that's how they're gonna get the profit. For the same purpose, the company has collected a data set from the sale of houses in Australia. The data is provided in CSV format. So the company is looking at a prospective properties to buy to enter the market, as I already told. You are required to build a regression model using regularization in order to predict the actual value of the prospective properties and decide whether to invest in them or not. So the later part, that is whether to invest on them or not, that is up to the company, but our job here is to do the prediction part. The company wants to know the following things about the prospective properties: which variables are significant in predicting the price of a value, how well those variables describe the price of a house, and also determine the optimal value of lambda for ridge and lasso regression. This is sort of a technical statement, of course, because this is not required for the company, but this is for our technical understanding. The business goal here is you are required to model the price of houses with the available independent variables. This model will then be used by the management of the Surprise Housing company to understand how exactly the prices vary with the variables, and they can accordingly manipulate the strategy of the firm and concentrate on areas that will yield high returns. Further, the model will be a good way for management to understand the pricing dynamics of a new market. So let's check out the code now. First of all, I have briefly mentioned the approach that I have taken here. First of all, we will import the modules, and here for this particular case study, I have divided the variables in two categories. One is numerical, one is categorical. So for numerical, for example, we will do the statistical summary, we can check out the distribution, we have to do also outlier inspection, we will do missing value handling, all these things. And we will also try to extract some new features, we will try to correct the data type if there is anything wrong, and we will also do the univariate bivariate analysis and some data visualization, of course. And for the categorical variable as well, we will do the missing value handling, encoding the categorical features accordingly. Sometimes it can be one hot encoding, sometimes it can be something else. Then we will also do the data visualization, dropping the redundant features. And next, after the data preparation, this is also kind of data preparation itself, like we will transform the target variable, we will input the missing value if there is any at this point, and we'll also do the feature scaling. Next, we will do the primary feature selection with RFE, and then we will go to ridge regression and lasso regression. We'll compare the model coefficients, and then we'll choose the final model to hand over to the company so that they can use that final model without getting to know about all the models that we built for our comparison and all these things. They will take the best model out of all our analysis. So moving on to the detailed part. So this is how I imported all the modules here. As you can see, I have kept all the modules at the top of my IP1NB notebook, so that if any time any module name changes for future, we can just come back here and we can just change the name just on the top. That should be fine, because the alias name we can still keep the same, but if the module name changes, it will be very easy for us to change it. Next, I have imported the data, read the data from CSV into a pandas data frame, and first I always try to see the info, which will give me a brief idea of all the columns. And as you can see, most of the features have 1460 data entries, and you can also see the type here. As we can see very quickly that there are 91 values present for the feature alley, means most of the values are not present. Okay, so it has 0, I think it starts from 0, yes, 0 to 80 columns are there, means there are 80 features and 1 target variable. Next, I checked out the describe, which is the statistical summary. We'll also check this out in details in the numerical variable analysis section. So after that, I just divided the data frame into two. One will be the numeric data frame, the other will be categorical data frame. So these are the numeric features we have. We have ID, MS subclass, lot frontage, lot area, overall qual, overall condition, year built. There are so many. So one of the things that we will do at first is checking for the outliers. So for this particular case study, I have considered outliers whatever values are present beyond the two whiskers of the box plot. So the lower value will be lower and higher value I have decided here. So this is the higher upper whisker value, which is 75 percentile plus 1.5 into interquartile range. Similarly, the lower range will be 25th percentile minus of 1.5 into interquartile range. So interquartile range, again, it is the difference between the 75th and 25th percentile. So that's how we are getting all the upper range and lower range, and whatever is there beyond those levels we are considering as outliers. So I'm just taking the percentage of values that are present beyond the limit. So as you can see, I just made one simple data frame which has one side, one column for the feature name and other column for the percentage of outliers. So we can see that there are lots of features having quite a few outliers. As you can see, there are some zeros as well, means no outliers in these features. So majority of the numeric features have outliers. Dropping all those features will cause loss of information, because of course we don't want to lose all of this data. There are definitely a lot of important features over here. So instead of dropping all these features, we will reassign fixed minimum and maximum values for those where we can see the values are more than the upper limit or less than the lower limit. So what we are doing here is, for the values which are above the upper whisker, we'll assign this value to them. Like, we'll reduce all those values to the upper whisker, and any value which is lying below the lower whisker, we'll take all those values and make them equal to the lower whisker. So nothing will be beyond that limit. That's how we are just capping and flooring the values. And of course, sales price, which is the target column here, is excluded for this, because we don't want to like do any outlier treatment for our target variable, which will be, if we do that, it will be very misleading. It will affect our predictions. So that's what I did here. And once that is done, again I'm checking the describe. Like now the drastic values will be gone. And for some features, as you can see, there is absolutely no variance, nothing. This is also because there is only one value throughout all the rows in these features. So probably we'll remove these features in a later stage. So this is why we should do the describe function, or we should see the statistical summary. Next, I checked out the correlation of the numeric data. As you can see, it's a huge heat map, and it's not very easy to like see, but as you can quickly see here, like there are some lighter patches for this color map. That lighter patches here will of course mean like very high positive correlation, as you can see 0.88, 0.83. So it will be a good idea to get rid of these features, at least one of them from the pair, so that we can get rid of the high collinearity present in the data set. As you can see here as well, we have quite some high positive correlation going on. So some of the features have high correlation with each other: garage cars and garage area, garage year built and year built, this and this. So first two, for example, what we saw from the correlation matrix, we can understand intuitively as well. Say for example, garage cars and garage area. If we have two cars, absolutely the garage area will be more. Or the people having two cars will of course choose a garage which has like bigger area. Or people having more than that will need bigger garage. In contrast to that, if people are having only one car, then they will have a small garage. So that makes complete sense here, isn't it? That's why these two features are highly correlated. Similarly, garage year built and year built. Year built means when the like property was built, and when the property was constructed, and when the garage was constructed. So if the property was constructed probably around 2000, so probably the garage was built around the same time as well, which makes complete sense here. So that is the reason you can intuitively also explain why these features have higher correlation. But if we try to do those things for all these many features, it will be very cumbersome and not very efficient, of course. That's why first to make the correlation matrix always helps us. So next I did is univariate and bivariate analysis. As you can see here, I have taken some of the features like MS subclass, lot frontage, lot area. These things you can again check the data definition. There will be a different CSV file available with the data set where you can see the meaning of all these features, which I am not explaining here because it's already available with the problem statement. So features like lot frontage, lot area, total basement square, I think this is the square feet, means the area in square feet, first floor square feet. These are showing positive correlation with sales price. Means say for example, total basement square feet, first floor square feet, second floor square feet. If these values are high, means the property is quite big. That means it is more likely to be more costly than other properties having lower values for the square feet or having lower area. If all the other features are probably not changing in that case. So these are having a positive correlation, as we can see, with the sales price. And MS subclass is discrete, as we can see here. It's just some random values. We cannot really make sense out of this. And for basement square feet 2 has single value and can be dropped. So for this one, as we can see that we cannot really make any conclusion out of this. That's why we can just drop this right away. Next set of features we took like this. Again, you can look out for the meanings in the data dictionary given along with the problem statement, and it's really easy to see that these features have no variance whatsoever, like with respect to the sale price. So since our main objective is to predict the sale price here, and there is no change in the values of these features, we can safely drop these features. And also we can see that here garage area here and garage living area, these two have a prominent positive correlation with the sale price. Means, of course, if the house has a large garage, it means that the sale price is going to be more. That's what our plot is telling us. Okay, next thing that I did is checking out the distribution of the numerical features. As you can see, here we have taken MS subclass, lot frontage, some of the things. Since there are so many features, you can always go with your intuition, like whatever you want to take, you can take, and some of the things you can leave out, because it's not possible to take everything in the visualization part. So I took these things. You can take a different subset as well, that should be fine. So after that, I'm checking the statistical summary again. Now removing the features having fixed values, as they won't contribute in predicting sell price. That's what I was mentioning earlier, that there is no variance whatsoever in these features, so we will just drop them. I dropped the features here, and this is the remaining features. And then we have some discrete value numerical features as well. So this means like 1, 2, 3 values like this, which are not continuous in their values, and for them we can just do bar plots. As you can see here, I have done bar plots for all the numerical features having discrete values. And let's check out some of the observations. So overall quality, it is actually like a rating. So more the rating of this feature means more the sales price, because of course if the quality is good, the price is going to be good as well. Next we have overall condition. Sale price is highest for rating 5. Means of course if the condition is good, means the sale price will be good as well. Similarly, month sold and year sold, sale price does not show a strong trend depending on the month and year on which it is in which the realty was sold. So of course it makes complete sense that it is not a very seasonal thing. The price of the realty is not seasonal. It depends on other features, but it definitely doesn't depend on the time it's sold. Full bath 2, half bath 1, this has the highest sale price. Means you can understand from this the costliest housing properties have 2 full bathrooms and 1 half bathrooms. So these are the things the company should look for, like which features. So first of all, when they are getting the houses in lower price, then they can improve on the features, like whichever feature is driving the sell price, so they can work on that, or they can improve those features of those low price houses they got. And once those are improved, then they can easily sell those houses in a much higher price. Because say for example, if garage area is one of the important features, I am just giving one example here. If garage area is one of these features, or maybe garage condition, say for example garage condition is one of these features which is very strongly driving the sell price. So first of all, they got all the houses having poor condition of the garage, so they bought those houses and they just remodel the houses a little bit, or did some improvement in the garages. So after that they will get very high prices when they are selling those back. So that's what I'm saying. Just we should get the idea of the features or the properties which are the main driving factors of the sale price, so that after getting the houses at a very low price, they can just change few things here and there in those things, in those important features, and after that they can sell them at a higher price. Next, moving on to the observations again, like total rooms above ground, I guess, more the number of total rooms above grade. Okay, this is grade. More the number of total rooms above grade, more the sale price. Makes sense, because again area will be more number of total rooms, again this will be like bigger houses, so sale price will also go up. Garage year built, year remote add, year sold will extract new features to identify any trend, because we are not able to see any trend from this plot. So we'll try to see if we can get something meaningful after extracting some new features out of them. Next we have basement full bath, kitchen above grade, need further inspection for meaningful insight, because we couldn't get anything meaningful from these plots. Next, I did the statistical summary once more. As you can see, most of the values are 1. So basement full bath, we have this kind of values. 2 and 2.5 are very little, like only 16 values out of like 1400. And kitchen above grade, all the values are 1. So we can drop this because there is very little variance in this feature for these two levels, and kitchen above grade has a single value in all rows, so we can drop that as well. Next we are checking the garage year built. So these features we are checking again because we couldn't get much information from the plots, so I'm just doing the statistical summary and converting the year related features into the number of years, because again, if it is given at 2015 or 2014, that cannot really give us much information in the plot. So better to make number of years from the current year. So from that it will be much easier to get the information in the plot. So that's what I did. We just changed it into number of years since the current year. See, from 2021 I just deducted this, and now we get some information at least. So for most of the realty properties, garage is built within the last 20 years. Sale price is more recently built. Sale price is more for recently built garages. Next is sale price is more, lower value of year built, more recently. Okay, so there is a for missing here. So sale price is more for the recently built houses, because of course those are the new properties, so price will be more for them. Recently remodeled houses, lower value of year remote add, have higher sale price, of course, because first highest sale price will be for the house that are newly built. Then the houses that are remodeled or renovated very recently, those will also have quite high sale price, because they are again like having the modern construction and so things like that, so they will also have high sale price. And next, year sold still does not show any significant trend. So as before, it's still not showing anything, so we can just safely ignore that feature, drop that feature. Next thing we are doing is missing value handling. So here I am checking for the percentage of missing value in the numerical features. These three we have got this 18%, 1%, 6%. Since this has 1% missing data, so we can just drop the rows having the missing data, will not lose a lot of information. But the feature having 18% missing value, for this one we will do some missing value imputation. Next, garage cars and garage area correlation coefficient high, so we are dropping them. So basically whatever we observed before in the correlation section, we can now drop those things because I didn't drop those things earlier because I still wanted to see the visualization part. So that's why once the visualization is also done, now we can get rid of the features having high correlation coefficient, and missing value imputation will be done for the features. Next, we are moving on to categorical features. Categorical columns are these ones, and now we have the percentage of missing value. As you can see, 94%. This is what we saw when we did the info function. So this one we have to just get rid of this feature, or maybe this one, or maybe fence. We'll check one by one and we'll do accordingly. So for alley, no value available means no access to value, actually. Sorry, and no access to alley. So that is one thing. And then, like, we can always do missing value imputation with respect to the particular feature. Say for example, alley, if there is no value available means we can understand that there is no direct access to the alley from the housing property. So we can just replace the missing value with this, not applicable, or this. Similarly, basement quality, basement condition, these things, NaN means no basement, because if there is no basement, in that case we cannot just populate this quality, condition, exposure, fin type, these things. So it makes sense if we just impute them with no basement or not applicable. Similarly, if there is no garage in the, oh my god, I cannot even pronounce this. I will go ahead with garage. Yeah. So if there is no garage, in that case, garage type, garage finish, garage quality, condition, these properties will not have any value. So that's why we can go ahead and make it as not applicable if missing value is there. Similarly, if if there is no fireplace, then we cannot have any value against fireplace quality. That is the thing happening for this missing value. So this makes complete sense to like populate these rows with not applicable. Okay. And next we have miscellaneous feature. NaN means no additional features are mentioned for these houses. So that's what we are doing is null sum. So first we are checking the sum of like all number of rows where there are missing values, and we are populating all those rows with not applicable, as I explained just now. Next we are dropping the features having high imbalance after missing value imputation, and we are also dropping the rows having low missing value count, because in that case we will not lose much information. Next, we still have one feature left with 18% missing value. We'll come back to that later. Next, we are generating the box plots, because we want to see the sale price for all the labels, right? So here I have taken a subset of the features, of course all the categorical features here, and as you can see, this lot shape, slightly irregular lot shape, have highest sale price. So you have to check all the labels and try to understand meaning from them. That's what I did. Utilities, most of the houses in the data set have public utilities. Land slope, houses at severe land slope have the lowest sale price. Maybe those are not really very popular, and people don't really like houses at severe land slope, so that is the reason they have lowest sale price. And house style, of course, two-storied houses have the highest sale price according to this data set. External quality, external condition, houses with excellent quality of material on exterior. Sorry, it's not external, it's exterior. Exterior quality is good means we will get good sale price, or condition and quality, there are two. Similarly, we have other things like heating quality, kitchen quality, functional, fireplace quality. So we can check the box plots for them as well. And houses having excellent heating quality and kitchen quality have the highest sale price. Typical functionality have the highest sale price. There are few houses that are severely damaged. That is also one of the important observations. Then we have sale price range is largest for the houses with average fireplace quality. Like people are not really bothered about the fireplace quality in that case. It's just a decent one should be fine. Similarly, we are checking for garage features like garage finish, quality, condition, as you can see. So we can take some similar or related features together to visualize as we have taken here. As you can see here, the sale price is highest for the garages that are finished, and range of sale price is widest for typical to average garage quality and condition, and there are few houses with excellent condition of garage. Next, we are checking the basement features. Since there are so many features, it's really good idea to take similar features together, as I have taken here the basement related features together, and the observations are like houses with excellent quality basement have highest sale price, good living quarters have the highest sale price, and a lot of houses have unfinished basement or no basement at all, label equal to not applicable. Next is encoding the categorical variables, because of course we have to do a regression model after that, so we cannot have these categorical features. That's why we have to like map all these features, encode all these features to numerical ones. That's what we did, and after that we are checking the features after encoding. Now we are checking out the unordered features like this one. So previous ones were like ordered, like there are good, average, excellent like this. That's why I have considered them as ordered. Now there are other features that are not ordered, like here. Here as well I have done box plots, and I will just go through some of the observations I had. So most of the houses do not have alley as we saw earlier, and we populated the rows with not applicable. And neighborhood has a lot of labels. Using so many labels will increase the number of features to a very high level, so that's why we will get rid of some of the labels that are not important. And houses classified as MS zoning equal to RL or residential low density have the highest sale price, means where it's not very congested. I think those are the houses having the highest sale price. Next, we are checking for some other features, and I'll just go through the observations. Normal condition, condition equal to condition 1 equal to norm. Houses are likely to have, like normal condition houses are likely to have highest sale price. Features like roof, something, exterior first, second have some labels with very few data, cannot contribute much in predicting sales price. So probably we are going to just get rid of them once our visualization is done. Next, I took another set of features, and again some observations are like houses with foundation of poured concrete have highest price. Houses with attached and built-in garage have high sale price. Most of the houses do not have fence, so fence equal to not applicable are the data entries. Then we have cell type and cell condition. Most of the houses are newly built. Houses with warranty deed have high sale price, and cell condition equal to normal lead to high sale price. Next, we are encoding the categorical variables. That is done, and adding 144 features to existing dataset will make the model very complex. So from the above box plot, for some of the categorical features only having label, only one label dominating over others. So that's what I'm saying, that the features having very high number of, like this one, very high number of labels. We don't want this many number of additional columns to be added to our final data set. That's why we'll just focus on the few labels that are most significant for predicting the sales price. That's what I told there. So next thing, once that is done, so dummies to drop, that's why we just checked the value count and we dropped the features having very highly skewed data. So after that we are just getting back our original data frame again, and then of course we'll split the data into training and test set, checking the distribution of sale price. As you can see here, excuse me, it's quite skewed, it's not normally distributed at all. So here we will make use of data transformation. As you can see here, I have used log transformation, np.log. This is natural log, so we have used log transformation for sell price. So it is reduced from this scale to a very different scale, and it's normally distributed as well. So otherwise we cannot really use the linear regression effectively. That's why it was necessary. Now we have the xtrain, xtest, ytrain, ytest. We are imputing the missing values after that. This we are doing after training and test set split, otherwise we will leak some information from training set to test set. That's why we are keeping things separate. We are also doing the feature scaling, that is, we have used standardization here. This is important for regression, because otherwise if we don't perform feature scaling, that means the features having higher magnitude will be perceived as having higher significance, whereas that is not the case always. So we are bringing all the features in the same scale, so that the features do not get misinterpreted by the model. So that's what I did. We did standardization with standard scalar, and this is how it looks like. Basically it's bringing down between -3 to +3. And then since we have a large number of features, before feeding them into ridge regression or lasso regression model, first we have done the RFE, and we will take initial set of features to begin with. So here I have taken top 45, 50 and 55 features, which is calculated through RFE, and next we will also check the adjusted R-square value for these three. So that's what I did for these three. And next, so here by inspecting the adjusted R-square, we found that top 50 features, it is a good place to start with. So we'll go ahead at top 50 here, and we will build the ridge regression model. So for ridge regression, we need to specify the alpha, or which is the regularization factor. So I have taken a lot of values, and we will see which is giving us the best. Okay, comparing the features. Okay, so here I have used grid search. Of course, we have to use some cross validation or some grid search or something like that to get the best value, to get the best estimator. That's how we got the best estimators, and we are comparing basically the best estimator for ridge and best estimator for lasso regression obtained from the grid search CV, and we are just comparing the coefficient values what we got. Next is we are building the final model. We are taking lasso regression because it produced slightly better R2 score on test data, because we can just compare the coefficients, but it will not tell us much like how we should take the final model. So because of that, we can evaluate the model based on its performance of the unseen data. So we just calculated the R2 score on the unseen data for both of the estimators, and we found out that lasso regression model is performing a little better than the ridge regression model, and hence we are taking this as a final model. And these are the coefficients of all the features in the final model. And yeah, so we can just sort values, and we can for this problem statement I have shown the top 10 features in the final model. And yeah, that's it for this case study. So this is the summary. This is what we did. First, the housing data is read and analyzed, dividing them into numeric and categorical features, and sale price is the target column. All the features are then analyzed, missing value handling, output, outlier detection, data cleaning, all these things are done. Trend of sale price is observed for change in individual features. New features are extracted like we did, and then we split the data into training and test. And since the sale price was right skewed, we did natural log of the same to make it normal distributed, and for model building it is used. And creating dummy variables is increased the number of features greatly. Highly imbalanced columns are dropped, that I explained earlier. And these are the top 50 features. First we got from the RFE, and next we applied ridge and lasso regression. And we also did grid search cross validation for getting the optimum value of alpha or the regularization factor. Oh my god, I cannot speak. Okay, so the optimum alpha that we got are 9.0 and 0.001, 0001 for ridge and lasso respectively. And model evaluation is done with R2 score and root mean square error, that too on the test dataset. So lasso we have chosen because this performed a little better than the other one on the test data. So out of 50 features in the final model, top 10 features will be first floor square feet, second floor square feet, overall quality, overall condition. These things we already saw in the data visualization section, that how strongly they are correlated with the sale price. Cell condition partial, lot area, basement, I think fin, I'm not sure what, square feet, cell condition normal. These are actually dummy variables we got. So first is the original feature name and second is the level name. Model coefficients are listed in a table along with the corresponding features, and that's what I did at the last. For example, natural log of sale price will change by this much with unit change in the feature of first floor square feet. Means, yes, of course, this is the model coefficient, right? So model coefficient always means that when all the other features are constant, unit change of that feature, that particular feature, will make change of this much in the target feature, target column. So that's what I am telling here. Negative sign means, of course, negative correlation, and predicted value of sale price is transformed into its original scale after performing antilog. So that's it for this case study. I hope you learned something from this case study. If you have any queries, feel free to comment down below in the comment section. And as always, like, subscribe, share, and yeah, keep on practicing other new case studies, and let me know as well what things I can do for my next case study. So that's it for today. Bye guys.